Hello students, our next video is on the enhancement MOSFET or E-MOSFET. The main difference between D-MOSFET or the depletion MOSFET and the E-MOSFET is that here you can see the similar figure of the MOSFET. Here there is no channel implanted on the E-MOSFET. Here this channel is the induced channel. This is the main difference between E-MOSFET and D-MOSFET. The construction is like this. On an N substrate, this is an N substrate on which two heavily doped P regions are implanted, P plus and P plus, on which this source and drain are inserted and the silicon dioxide layer is formed, and this is the gate terminal. Now initially there is no channel, and when we apply 0 voltage on the gate and if we apply drain and source with a positive potential, there is no connection between these two regions. Hence no current flows when VGS is 0, and even if we apply VDS, there is no current is passing through the substrate. Now what happens when the gate is given a negative voltage? When the gate is applied a negative voltage, an electric field will be directed perpendicular through the oxide layer. So here the positive and here a negative, and a P channel is induced. It starts induced between the two P plus regions. So this induces an inversion layer of minority carriers. Why is it so called inversion layer? Since this is an N substrate and P is induced, or the holes are induced, which are the minority carriers in the substrate. So this induces an inversion layer of minority carriers, that is holes on the N substrate. Refer this as in N substrate. This is strongly marked as P substrate. It is actually the N substrate. Now when VGS increases or it becomes more and more negative, this channel starts to build up. A channel starts increases from this P plus region to this from source to drain, and finally a channel is formed between the source and drain. So when VGS is more negative, induced channel of positive charges increases and the conductivity increases and ID starts flowing. Right? Thus the drain current is enhanced by the negative gate voltage. I repeat, thus the drain current is enhanced by the negative gate voltage, and hence this device is called enhancement MOSFET. This is the circuit symbol: gate, drain and source. Here there is a breakage in between the region on this line, and this is the section where the substrate is connected to the internally connected to the source, and this is a 3-terminal figure. Now next is the drain characteristics or the VI characteristics. Here we can see that only negative voltages are represented here. That is why, because when VGS is equal to 0 or other than any negative value, there is no current flow in the channel. That is, when VGS is equal to 0, there is no current, since there is no connection between drain and source. And when VGS is made negative, ID starts increasing slowly and linearly and then becomes a constant. It starts increasing linearly and then becomes a constant from -4, -8 to -20 volts. This is the VI characteristic or the drain characteristics. Now it reaches VGST or VT. It is the gate source threshold voltage at which ID reaches a definite small value. Okay, so this is the transfer curve and this is the value of VGST. This becomes a definite small value, 10 microampere. This value is called the gate source threshold voltage, above which ID starts increases with VGS, and this value ID on. This is the maximum value of ID. Next we look into a process which I have told earlier, the ion implantation. The ion implantation technique demonstrated in the figure which we discussed 10-11 provides very precise control of doping. Ions of the proper dopant such as phosphorus or boron are accelerated to a high energy of up to 300,000 electron volt and are used to bombard the silicon wafer target. The energy of the ions determine the depth of the penetration into the target. In those areas where ion implantation is not desired, an aluminium mask or a thick 12,000 Armstrong oxide layer absorbs the ion. Virtually any value of Vt can be obtained using ion implantation. So this is the process of ion implantation in brief. So this is the process by which a thin layer, such thin layers of silicon dioxide or the channel in the depletion Mosfet can be implanted. This is the process by which such precise doping is done.